So we're going to start limits today. And if you notice this, it tells you which problems you can and can't use a calculator. So if you want to go ahead and get your calculator out, there's some calculator work on this, but there's not a whole lot. This right here is how I'm going to tell you that we're going to use a calculator. You know, on the AP test, you're going to have parts with and parts without, and I'm going to show you what a full-length AP test looks like in the next couple of weeks, and you've already seen the questions, but you'll see kind of how it's split up and everything. So let's just go ahead and get started. So limits, you may not remember a whole bunch about limits, I don't know, but looking at problem number 1, if I want to know what is the limit when x is approaching 2, what should I do with that 2? Plug it in. Alright, so I'm going to plug in 2. I get 2 squared minus 3 times 2 plus 4,
2.
And that is 2. Now this is a pretty straightforward limit problem. There's no weird things going on or anything like that. Okay, I'm going to skip certain problems. Those are, you just get everything we don't do in class today, that's your homework. Okay, so I'm going to skip 2 because it's very similar. So let's look at number 3 now. So if we try this plug-in strategy on 3, something interesting happens.
0, 0.
Yep, we end up getting 0 over 0. And when you get 0 over 0, that means that the limit does exist, but you are going to have to do more work to find it. When do you know the limit doesn't exist? Not when it's 0 over 0, but when it's some other number over 0. Okay? Graphically, 0 over 0 is a whole, and we know we can have a limit at a whole. If we were to have like 4 over 0, that would be a vertical asymptote, which does not have limits. It has one-sided infinite limits, but it doesn't have a limit. All right, so what we need to do here is we need to redo the limit, but algebraically remove this whole. And the easiest way to do that on these problems is factoring. You may remember this. There were other algebra things, although the AP test really sticks with certain ones, and that's what we're going to really review. Okay, so cross off the x plus 5, and now when you plug in -5, what do you get? -10. So when you get 0 over 0, there is a limit. You need to do something algebraically to cancel something out, and you get then your answer. Okay? I am going to show you something new actually now. So this is not meant to confuse you, and you're actually, everybody today has been like, oh, this makes things easier. And there is something called L'Hopital's rule, and it's spelled weird because it's not English. Yeah, it looks like hospital. Yeah, there's no S, but some spellings do have an S, but it's still always L'Hopital's because it's like French. All right, if you want to think of it that way. So L'Hopital's rule, although you wouldn't do apostrophe S in French, that's not, but whatever. Okay? So really, when I write this anytime moving forward, I'll probably write LHR. Right? I don't really care if you know what its name is. This is a BC topic. But it's going to make certain questions easier, and this is one of them. So on 3, I'm going to call it 3B. All right, and so what we can do is, and this is something you can do anytime you're taking a limit of a fraction. Okay, it has to be a fraction. So I could not have done what I'm about to show you. I could not do on number 1. Okay, I could do it on any of these, though, that are fractions. All right. I can say that the limit of the original fraction is the same as the limit after I take the derivative of the top and the bottom. So the derivative of x squared minus 25, what would that be? 2x. Derivative of x plus 5, 1. All right, now when I plug -5 in, there's no whole or anything to worry about. Okay? -5 goes in for x, and we can see that that does give us -10. So you may be wondering, Ms. Brooks, why did you never show us this before? Well, when I taught you limits, did you know how to do a derivative at that point?
No.
No. Okay? You might have, but I hadn't shown it to you yet. And so when we did limits, all we knew was our good old pre-calc skills. We didn't know about derivatives. And so, like I said, this is something that BC kids have to know, but I don't want I want you to have all the advantages you can get. This is going to make certain problems easier for you, especially like if you're horrible at factoring, this is something you want to do. All right. So let's look at, you can do that when you're doing a limit of a rational, yes. Now, there are limitations to this, and I'm not teaching a whole lesson on this, but I am going to show you a few ways that it would make, this is where I want you to use it. All right? If you're not sure you can do L'Hopital's rule on a certain problem, then don't do it. So if we look at 4, there is an infinity right here. All right, so let's first talk about how we did 4 before. All right, limit as x approaches infinity. We're talking way far to the right. This is a horizontal asymptote. That's what they're really asking you. So we had Bobo, Bot, and Betsy. Bigger on bottom, y equals 0. Bigger on top, none, or infinity. Bottom equals top, coefficient. Or you had, if the degrees are the same, play the coefficient game. Low over high.
0 equals y.
0 equals y. I can never remember that one. Okay, so you have all of those things at your disposal. That's what you're going to do when you're talking about limits as x approaches infinity. So what's the deal with the degrees on this one?
Coefficient.
Yeah, degrees are the same. So what we would do is we would do the coefficients. 1 divided by 1, which is equal to 1. Okay? If the degree on top was bigger, what would be my answer? What makes sense? If the top is growing at a much faster rate, there's a slant asymptote, so what would the limit be? You could say infinity, or you could say the limit doesn't exist. All right? The 0 is when maybe like the denominator was x cubed. Okay, but let me show you what this looks like with L'Hopital's rule. So if we were to do the same problem, we have the limit as x approaches infinity. If we were to take the derivative, I would have 2x minus 3 and 2x minus 1. Now this is still not clear, maybe. Maybe it is, maybe it's not. You've forgotten the rule. So let's do L'Hopital's rule again. It's still a fraction. All right, so that would give me 2 over 2, which is the same as 1, and that's what the answer is. It doesn't even, there's no x to even plug in at this point. That is just 1, is what we got. So this is another way L'Hopital's rule could be helpful. So let me go back to what we were saying before. If the numerator had a higher degree, and I was doing the derivative, I would still have an x on top, right?
Yes.
Does that make sense?
Yes.
If the degree was higher in the numerator, there'd still be an x, so maybe it was like x over 2 or something. Well, what happens when you plug in infinity in for x? You get infinity. So in infinity, that's not a limit, okay? You could write infinity or you could write does not exist. If the degree on bottom were bigger, what you would end up having here is something like 1 over x. And think about this. What's 1 over infinity? Really small, so 0. So this you may or may not want to use L'Hopital's rule on these problems. If you know your rules really well, you may not even want to mess with it, okay? But it's there. I wanted to kind of show you, and I'm going to give you one more. Before I do another problem on here, I want to give you one more example for L'Hopital's rule, and that is, sorry, let me write this here. The limit as x approaches 0 of sine x. This is not on your packet. You're just going to have to write this. I meant to include it. I forgot. So the limit as x approaches 0 of sine x over x. So without L'Hopital's rule, with just this is how we have limits plugging in 0. What happens?
You get just 3 over 0.
You get, yeah, sine of 0 is 0, and you get 0 over 0. But can you factor sine? No. Algebraically, you are out of luck here. So this is one that you would have to use your calculator on, unless you use L'Hopital's rule. So let's do that. Limit as x approaches 0. Derivative of sine is cosine. Derivative of x is 1. And now when you plug 0 in, cosine of 0, you get 1. And that's the answer to this one. Okay, so here's just another example. This is not something you're ever going to have to use on your test. Like if they gave you this, they're going to let you use a calculator. But I just want you to have everything you need. And this is, once you know derivatives, this is just a really easy thing to do. Now, I couldn't have really taught this to you before, but now I can. All right, let's look at number 7. So this is a piecewise function, and we know that when we have piecewise functions, sometimes they meet and sometimes they don't. Okay? In order to have a limit, these two pieces have to meet at x equals 0. So you need to plug in 0 to the top, you need to plug in 0 to the bottom, and this should also be x approaches 0. You know, these two things should line up. If not, you're still going to plug 0 in, but they're going to line up. We're going to see this happen every time. So plug in 0 to the top, you get 2. So that means that the top piece stops or starts at the point 0, 2. What about the bottom piece? Negative 2. So do the two pieces meet? I mean, are these two numbers the exact same? No, the two pieces do not meet, therefore my answer is the limit does not exist. In this case, the left-sided and right-sided limit are different, and when that happens, the limit does not exist. Alright, let's look at number 11 now. So number 11 is our first calculator. I would like to go ahead and approach this like how we've done the other problems, which is let's plug 0 in for h. So that would be e to the 0 minus 1 over 2 times 0. And what does that simplify to? 0 over 0. So some students might pick e. Say, oh, 0 over 0, that's not a real number. That limit doesn't exist. But in fact, this means the limit does exist. We just have to do more work to find it. You can't factor though this. You can't do that. So what they're saying here is, oh, this is going to be on the calculator part. Okay, so I'm going to show you or remind you how to use the calculator for this. Alright, so the first thing we need to do is actually go into y equals and plug in our equation, and we need to make sure that when we plug this in, that we use parentheses and make sure that it looks exactly like how it does on the paper. So that means putting that divide by 2x, that's all got to be in the parentheses. And when I press enter, it should look here exactly as it looks on my paper. And I'm using x instead of h. You could graph this and try to do it that way, but what I showed you before and what I'm going to remind you of now is the table is actually going to give you a more straightforward answer. But you're going to have to manipulate the table because when x equals 0, there's not going to be a value there. Okay, so let's go to the table set, which is diamond F4. And let's make sure our table starts. This is diamond F4, by the way. Let's make sure our table starts whatever this h or x value is. So it has to start at 0. But I need to get a lot closer to 0. So I don't want my increments to be by 1 because that's too far. So I'm going to make this become a really, really small number. So like 0.0001. And what I'm going to do is I'm going to make the table show me what are the y values when x is really close to 0. You do have to press enter 2 times here, once to kind of like enter it in and once to save it. If you don't do that, it won't, your table won't look like that. So now we're going to do diamond F5 and go to the table, and I'm going to hit up a couple of times so I can see what's happening. So if we look at when x is 0, y is undefined, that's the hole there. That's the 0 over 0. All right, but as long as the y values right here, above that undefined and below the undefined are close to each other, then that's our answer. So which is our answer here? 1/2, B. Okay, that's as easy as it is. You can do any limit problem this way. So on the calculator part of the test, use this if you need to. If one of these was 0.5 and the other one was negative 0.5, what would that tell us about the limit? Doesn't exist. And if these numbers look like they're kind of getting close together, but maybe not, then you just need to make that increment even smaller, like 0.0000000001. The smaller that number is, the more clear what your answer should be here.
The y values were close though, wouldn't it just be like a real number over 0?
Well, yeah, it would be we would have gotten a different result here.
Yeah, okay.
Yes, you're right about that. Okay, so now let's look at how we could do this maybe with L'Hopital's rule. Because, so there's L'Hopital's rule. Because I just want to get the practice in. So the limit as h approaches 0, and we would take the derivative of the top, take the derivative of the bottom. So what would the derivative of the top be? Just e to the h. And the derivative of the bottom would be 2. And so now let's plug 0 in. We get e to the 0 over 2. E to the 0 we know is 1/2. So you may be thinking, I hate the calculator. I don't like it at all. I want to use this. Great. And you may hate this and like the calculator. Everybody's different, but I just want to make sure you have different ways to do these problems. Okay, any questions about how to use L'Hopital's rule? All right. Turn the page, and let's look at, we're going to kind of look at 14 and 15, although I'm just going to work 15. Sure. So this says, find the value of k if it exists that will make each function continuous at x equals 1. Does this type of problem look familiar?
Yes.
Depends on your memory, I guess. We did a whole lot of these first semester, and it was on your after party, like, I think, at least, like every other one for a while. So I'm going to work 15, and I'm going to mention something about 14. What we're thinking here is, okay, I have two pieces to my piecewise function. I have a parabola, and then I have a line, but I don't really know, I can't graph this because I don't know what the y-intercept of that line is. And I want these two pieces to equal each other. And specifically, I want them to equal each other when x equals 1. So again, kind of like the limit problem, but this is not exactly like a limit. It's continuity, they're related. And so I'm going to plug 1 in, 1 squared plus 7, and that's got to equal the other piece when you plug 1 in. And then the direction said to find k, so I find k, and k is equal to 7. And if you wanted to check this, you could by graphing it, although I'm pretty sure I did this right, so it wasn't too messy. On number 14, what's going to happen when you plug 1 into the top piece? Whole. So you're going to have to factor. Okay? You cannot use L'Hopital's rule here because this is not just a limit problem. All right, so you only use L'Hopital's rule when it says limit of something. All right, taking the derivative of the top and the bottom changes it. It just doesn't change the limit. That's why we can use it all limit problems. All right, let's look at number 17 together. So number 17 is a multiple choice question. This was on a past AP test. It says the graph of the function f is shown at the right, which of the following statements about f is true. And I can see here that we have limits, and we have this little x equals a and x equals b here. So let's just go through the choices. Choice A says limit as x approaches a of f of x. Okay, so let's stop here and find this. So when the x value is equal to a or near to a, what is the y value near to or equal to? 2. And it actually equals, but even if there was a hole here, we would still say 2. Okay, what about the limit as x approaches b?
3. It's not.
What is the limit as x approaches b? Does it exist or doesn't it exist?
No.
It doesn't exist. Why not?
It's not a hole, it's just a jump.
It's a jump. The left-sided limit is 2. The right-sided limit is 1. So if this little b here had a little negative in the exponent, this actually would be a true statement because the left-sided limit is 2. And so I'm going to talk more about left and right side of limits in a minute, but A is definitely not true. Okay, I want you to read through the rest and see if you can figure out which one's true. You were listening really well. Yeah. Okay, what's the answer?
B.
B. Very good. Okay, so there's going to be questions on the AP test that are kind of hard, but then there's going to be some like this that are pretty easy if you just know what a limit is. All right, let's look at 19, because 19 starts using this other word, differentiable. So 19 says the graph of the function shown above, but really it's shown to the right. At which value of x is f continuous but not differentiable? Okay, so we want yes on continuity. So let's get rid of the ones where there's no continuity first. Okay, so which answer choices could I get rid of? B is not continuous. What else? C is not continuous. There's a limit at C, but there's no continuity. All right. What do you think about the endpoints? Can you say there's continuity at the endpoints? Kind of weird. So I'm actually going to put a question mark here and here. All right. I'm thinking continuity means it goes continuously through. I don't know. Endpoints, maybe there's continuity, maybe not. So what I'm saying is, if you had no idea what to do next, what would you guess? D. All right. This is how you take a test when you're not sure what the answer is. You get rid of the ones you know are wrong. You make an educated guess. We are going to go further. So, does anybody know the answer of where this thing is not differentiable? Like for sure? And tell me why?
D, this is a cusp.
At D, we have a cusp. Now, if you remember, differentiability, differentiable, has to do with derivative. And derivative is the slope of a tangent line. So at a cusp, you could draw a tangent line that way, you could draw it that way, you could. There's no smoothness to that curve, so there's no derivative at a cusp, which means it's not differentiable. So that's how we know for sure the answer is D.
It has to be closed off D,
It doesn't. If there was, are you saying if there was a hole at D?
Yeah.
That's C.
So
Like,
if there was a hole at D, we would have gotten rid of it as an answer choice based off of the continuous. To be, though, differentiable, it has to be continuous.
okay.
So, like, they could have not even said F continuous. Well, no, they would. I guess the way they have it here is good, but if something is differentiable, it has to be continuous. So if there was a hole there, it was not continuous. It's definitely not differentiable. Good question. All right, turn the page. And let's look at this next problem set here, 22 through 27. All right, so this is talking about one-sided limits, and you may or may not want to like outline your x and y axis because I think it's kind of hard to tell sometimes on these photocopies. And you're going to be needing to count these, so you need to know where you're counting from. Okay, so 22 says the limit as x approaches 2 from the left. All right, so here's x equals 2. On the left side or from the left, the graph is shooting straight up. So what y value is that? Infinity. So that limit does not exist, but we would write infinity. And if this was multiple choice, they're not going to have infinity and does not exist as answer choices. You don't really have to worry about that. But they would probably here they're looking for infinity versus negative infinity. All right. So let's look at the next one. 3. Okay, so we're at 1, 2, and here's 3. And 3 from the right looks like the same as 3 from the left, which looks like 3. There's at x equals 3, it's just a normal old point, nothing special, nothing crazy. So what's the limit? -1 for both the next two answers. 3 from the right, 3 from the left, and just 3 all have the same limit. When the left-sided and right-sided limits are the same, that is just the limit without the plus or minus. Okay, so 5 is the next one. The limit as x approaches 5 from the left, that would be up here. Even though there's a hole there, that's okay. You can still have a limit at a hole. 1. And what about 5 from the right? Negative 1. So does the limit as x approaches 5 exist? No, just 5. No, because these two are different. All right, and then what about 27, the last one? There was a hole here, but it doesn't matter. 0. Okay, a big mistake students make here is when they see holes, they say, oh, the limit doesn't exist. But the limit can exist at a hole. That's not continuous, but the limit does exist. So you just have to kind of keep the definitions of those words. Actually, turn to the very, no, sorry. 33 is the next one we're doing, whatever that may be. Here we go. Like these down here, it's really, I think, hard to tell where the axes are, so I would go with highlighter or something like that. Okay, so 33, last problem that we're going to do together. Says, which of the following is a necessary and sufficient condition for a function f to be continuous at the point x equals 4? And if you look at this, it doesn't say anything about holes, asymptotes, cusps. This looks very formal. So we need to remember our definition of continuity, the formal calculus definition. And I'm going to give you a hint. There's 3 conditions. Okay? Well, I'm going to go through these because I found today people, after I write it, they're like, oh yeah. Okay, first of all, the limit as x approaches 4 of f of x has to exist. That has to be true, which means the left and right-sided limit have to equal each other. That's implied by saying that this limit exists. What else has to exist? Well, that's what we're trying to prove here.
Oh.
The point. So f of 4 also has to exist. Okay, the limit can exist with just a hole, but if we want continuity, we also have to have a point. And then the last thing is they have to be the same thing. You can't have, like, I'll just say this. Okay, there we have a limit, and here we have a point, but if they're not the same thing, you don't have continuity. So 3 is saying, okay, well then the limit as x approaches 4 of f of x has to equal f of 4. Okay, so now we kind of have a weird thing because I'm looking at my answer choices and I see all 3 of these. Okay, but B and E are like totally wrong, so I'm going to cross those off. So if I can't have 3 right answers, so I need to read this. Again, which of the following is a necessary and sufficient condition? So what are they really asking us when they ask us, is this sufficient?
Kind of the best of both worlds.
Yeah, which one takes into account the other ones? If you can only pick one, which one will be good enough? Yeah, D or 3, okay? Because if I'm saying that the limit as x approaches 4 of f of x, if I'm putting that in there, it has to exist. And if I'm saying that equals f of 4, I'm saying that has to exist. All right, does that make sense? All right, so the rest of these are your homework, and this should be done by Monday. I know it seems like a really thick packet, but a lot of these are like true, false, and really simple, and most of the rest of them are even multiple choice.